Today we want to look at how to calculate the work done in stretching or compressing a spring. So the idea is we're going to charge that spring up with some mechanical potential energy. If you compress a spring or stretch it and then let go, it's going to start moving. It's going to turn that potential energy into kinetic energy and start moving. Now, the reason this requires calculus is because of the way springs behave. We're going to use what's called Hooke's law, which says that the more you stretch, the harder it gets to stretch, or the more you compress, the harder it gets to compress. And that's why you see here that the force required there is K times X, where X is the amount you've stretched or compressed. So that force is getting larger and larger and larger as the amount of stretch becomes more and more and more. So we're going to have to integrate to accommodate the fact that the force is changing continually throughout there. So let's look at this in general first and then maybe do a concrete example. So let's draw our spring. So what I'm trying to draw here is, say we have some spring, it's attached to the wall there, and it's just sitting there. Hasn't been stretched or compressed at all. So this I'm going to call natural. So that's our spring at its natural length. And then we're going to make this as general as possible. So the initial configuration of our spring might be that it's already had a little bit of stretch. Now, in the statement of Hooke's law, it says compression or stretch. They're sort of symmetric, but most of the problems we'll look at it be stretching. So I'm going to draw this as a stretch. So say it has some amount of stretch already. This will be our initial. And then this is our final. So the idea is, this is what the spring would look like if nothing had been done to it. We're starting off some stretch already, so there is some potential energy in there, because if you let go at that point, it would start moving. So it's already got some energy stored in it, and we want to look at the difference from the amount of energy this has to now at this new amount of stretch. What's the energy difference? How much energy have we put in? So when you look at Hooke's law, you see that the key thing is the variable x there is the amount of stretch or compression. So when you think about your coordinate system, I'll draw an axis along here, x. That x is going to represent the amount of stretch or compression, so I should put natural length 0. When the end of that spring is right there, there has been no stretch or no compression. And then the initial will start off at some x value a and end at some x value b there. Okay, so here's the problem. Stretching from there to there, the amount of force is changing the whole time according to Hooke's law. So as we always do with integration, we'll partition that interval and think of it as a bunch of little poles. Each one of those little poles, we will assume that the force required was constant, even though it's actually changing, as Hooke's law says there, with respect to x. So the idea is you partition from A to B, and on one of those, let's just look at the work done just over one little subinterval there. So as we move from x sub k minus 1 to x sub k. And the idea is we'll assume that over that distance, the force was constant. So the little bit of work done, remember now work computationally is force times displacement. So we're going to have some force in pulling that spring, and the displacement here is delta kx. Well, what is the force? Remember, we always assume our function is constant, and we usually take some value in that subinterval, c sub k. So the work in that little bit of stretch there, I'm going to call w sub k. It would be approximately the force and we'll take the force at c sub k. So that's why it's approximate, because we're assuming the force is fixed, but even over that little pull, the force is changing. And then the displacement, well, how far are we moving it? Over that little subinterval, we're moving just a little delta x sub k. That's the idea. So we know then from Hooke's law, right, what this force is. It's k times the x value, which is c sub k in this case. So I'm going to fill in the details of Hooke's law. K times x, so k, the x value we're taking is just our c sub k delta x sub k. Now, as always with calculus, we've got this guy, which would be just one of our subintervals, but from A to B, there'd be a bunch of those, right? There would be n of those little pulls. So the overall work done in moving from that initial position to that ending position would be the sum of all these little works, approximately. And then, as always, we make that exact by taking the limit as the norm of the partition goes to 0. Remember, that's our calculus way, our formal calculus way of saying, now chop this up into more and more and more subintervals, making them shorter and shorter and shorter. And then this approximation of assuming force is constant over the subinterval becomes less and less of an approximation, more and more exact, because you're taking it over tinier and tinier intervals. Well, that is our definition of the integral. So it's the integral from A to B of, here's our W, and that's our work integral in stretching a spring. Where you started to where you finished, and then the force is really coming in here. That's coming from Hooke's law. A couple of things to be careful of here. First of all, x is amount of stretch or compression. So when you're thinking about your coordinate system, these values really need to be in relationship to natural length. So if the spring itself is already 2 meters long, then 3 meters is only 1 meter of stretch. So you got to keep that in mind. And we'll emphasize that when we look at a concrete example as well. Another thing is K. What is this K from Hooke's law? Well, it is the spring constant, right? So you know just intuitively or from experience that different springs have different resistance to stretching or compressing. And a K is the physical measurement for that particular spring. So a small K means really easy to stretch. So the spring inside your clicker pen, real easy to stretch, that'd be a very small K. The spring in the suspension of an 18-wheeler, very hard to stretch or compress, that would be a very big K. So in our problems, we need to be told what the spring constant is or given some information so we can figure it out. So this is a property of the individual spring. That'll change from problem to problem as the spring changes. But every time you're just integrating from where you started to where you finished, that spring constant times x. So in the next video, we'll look at an actual example of calculating that work.